So, Sina, you can start recording. We're gonna start your. So today our speaker is Sina Gholamian. He's a final year PhD student from the ECE department working with Paul Ward. He works on exploring approaches to automate, building automated approaches for analysis of software systems. And he is an NSEC doctoral fellow, or received the NSEC doctoral scholarships. So Sina, please, the stage is yours.
Thank you, Samar, for the kind introduction. Hello, everyone. This is Sina here, and today I'm glad to present to you my research, which is entitled as the login statement analysis and automation in software systems with data mining and machine learning techniques. So let's first review the agenda for today. I have categorized my presentation into three main parts. In part one, I review a survey of logging and its applications in software systems, which is divided into subsections. The first one is analyzing the log statements in the source code. And the second part is on the analysis of log messages in the execution log files. Then in the second part of my presentation today, I will talk about the log statement automation that is in the source code, which also has two subparts: log location prediction first, and then after that, I review log content prediction. And in the last part, part three of my talk, I will discuss the application of natural language processing, or NLP for short, for automated analysis of log files. That also has two subparts. In the first part, we show that log files are natural and local, and that enables us to apply NLP methods for automated log analysis. And in the second subparts, we perform a study on the logging costs and benefits in distributed systems such as Spark. So to give you one slide and summarize my contributions, I will say in part one, with a survey of logging techniques, we expose research gaps and provide concrete opportunities for future work. In part two, we automate the logging process in the source code, which saves developers time and improves the quality of logging statements. In part three, we enable and utilize NLP approaches for automated log file analysis, which help developers and practitioners in quicker automated troubleshooting versus manual analysis of log files. So first, motivation. Why logs? The important question is why we use logs. First, developers and practitioners spend a significant amount of time writing and reviewing logs. For example, log files are widely used to record runtime information of software systems, and the rich information of logs enables system developers and practitioners to monitor the runtime behavior. From the industrial perspective, there is an aggregate market cap of 100 billion USD in commercial log analysis tools. For example, Splunk, one of the key players of the field, adds up to around 20 billion USD market cap. And thirdly, logs are readily available, meaning that they don't need an extra hardware for functioning that instrumentation, for example, needs. And there is also no perturbation impact which instrumentation suffers from. So before I go into more details, I just provide some terminology. Log printing statements, also short for LPS, are in the source code, also known as log statements or logging statements. Is a logging code that is developed by developer and it's inserted in the source code. Log message, typically a single line, is the output of the LPS in the log file. And a log files is a collection of log messages stored on a storage medium, also called event logs or execution logs, or simply just logs. So with that introduction, I go to the first part of my talk today, which I provide some details on the first part of the survey of logging and its application in the software systems. So first, why we need a survey? So the answer is because there is no recent prior work to systematically review and categorize the logging research. It's valuable to show gaps in the current state of the research and enable its advancement. I should also mention that we received early feedback from a peer-reviewed submission that we had, and the feedbacks are encouraging and comments on the appropriateness of the survey to the field. So what is the general process of creation and analysis of logs? In this figure, I have an end-to-end framework that shows a creation process and analysis of logs. After the system architecture is decided, programmers implement the source code with logging statements, and the operators run the system with selected proper runtime configuration. I should also emphasize that the configuration parameters have direct impact on the amount of generated logs. For example, we can set the verbosity level as trace instead of info and generate more logs. While the software is running, events that are logged in the source code generate log records, which is saved inside the log file. Next, admins, developers, or practitioners, or even automated log analyzer tools can review the files and feedback the outcome to the designers, programmers, and operators to make adjustments to the architecture, source code, or system configurations if needed. And yes, so our survey is very long. So here I have tried to summarize it in a high level in one slide. After the introductory sections in the survey, in section 3 of the survey, we have pointed out the quantitative and qualitative costs and benefits associated with logging. Quantitative cost is the cost on computation and I/O resources of the system, and qualitative cost can be, for example, exposing private information of the user through log files. In section 4 and 5, we discussed logging, statement automation, and mining, which basically aims to understand current logging practices and use the findings to improve the log printing statements with automated log insertion and learning to log approaches. In section 6 of the survey, we reviewed the mining of log files. This provides insight on methods and tools to analyze log messages and log files. And this can be further divided into log management, log parsing, and their applications, such as system anomaly detection through log files. In section 7, we have reviewed the emerging applications of log, which is the recent interest in logs in other domains, such as mobile devices and big data. And finally, in section 8 of the survey, we have listed the future directions and opportunities for each categories of logging research. To also provide you some perspective, my research, which I explain in parts 2 and 3, tackles logging cost, automating log printing statements, and log file analysis, which are 3 main parts in the survey highlighted in red. This also shows how performing the survey has been insightful for me to find missing pieces of the puzzle and advance them. So to summarize the contribution of the survey, we have reviewed a large number of conference and journal papers that appeared on top-level peer-reviewed venues. We draw high-level trends of logging research and categorize publications into subdivisions. We examine each discussed research in details and highlighted the pros and cons of each one. And we also provide a set of challenges and opportunities that will lead the researchers in academia in moving the field forward. So with that, I'm finished with the first part of my presentation, that I move the second part. I think it might be a proper time to ask if there is any questions. Okay, so if there is no question, I move on to the second part. Now in the second part, I present our approach for automated log statements, automating the log statements in the source code with application of code clones and NLP, which is short for natural language processing. So let's first review an example of logging statements. On this slide, I have an example of a logged catch clause from Apache Hadoop project. There are 2 logging statements with different verbosity levels. One of them is debug, the other one is warn on lines 5 and 8. Additionally, logging statements contain a description, as you can see, authentication exception, and also some optional variables here. So this logged information in the catch clause will be useful to the developers at the time of debugging in case an exception happens. So now I also previously mentioned that we utilize source code clones for log automation. So let's briefly review what are code clones. Code clones are syntactically similar code snippets with equal semantics, as there are four main categories of code clones. Here I have an example of a Fibonacci function ranging from simply copy pasting a code snippet, which is type 1 highlighted here, all the way up to type 4, which is two code snippets that are syntactically very different but semantically equal. For example, now I have highlighted in line 37, we present a non-recursive for loop implementation of a Fibonacci function compared to the original one, which presents a recursive version. So the problem we are solving here is to find the set of method code blocks, CBM, which require a login statement. In addition, after predicting that a login statement is required, we also aim to predict its description, or LSD for short. And the solution is by utilizing code clones, as we hypothesize that code clones should be consistent in their logging statements, meaning that if there is a logging statement in the original method definition, MO, then all the MXs, which are clones of MO, should also have a logging statement. First, we had to do preliminary analysis and confirm our hypothesis that code clones are consistent in their logging behavior. Thus, we performed experimental evaluation on a set of open source Java projects. And our findings are that 98% of clone pairs are consistent in their existence of a logging statement. We also found that the majority of clones are type 3 or beyond, which means that although code clone syntax are different to a good extent, they still follow similar logging patterns. These confirm our hypothesis that code clones are consistent in their logging statements and can be used for a log prediction. Here I briefly go over the steps in our toolchain for log-aware clone detection. In step 1, we obtain source code Java projects from their Git repositories, and we have selected 7 open source Java projects. In step 2 of the toolchain, we extract methods definitions containing login statements from their abstract syntax trees. In step 3, we perform code clone detection on the extracted methods. Clone detection tool extracts source code features from the method definition, and the features are fed into a deep learning neural net model. The model predicts if two code snippets are clones or not, which we then use for log statement prediction analysis. In step 4, we perform our analysis on the results of the clone detection and collect stats on the clone pairs and types. So I mentioned that we use clone detection tools based on matching the source code features for different snippets of the source code. However, these features are not properly tuned in general purpose clone detectors to understand log estimates. Therefore, we updated the features listed in the table to be log aware to achieve a higher log prediction performance. The practical scenario is that assume MI has been previously developed in the code base. Now, another developer is implementing prime J at a later time. Therefore, our automated tool prediction approach tries to find a clone pair for a method which doesn't have a log statement yet by finding its clones in the code base which contain a login statement. In summary, the log-aware features are updated in a way to match the clone pairs regardless of the existence of the log statements, which fixes also shortcoming 1 and 2 from the general purpose clone detectors, which is high rate of false positive and false negative cases. Now we move on to show some prediction results. The table here summarizes the projects that we use for our experimentation. We show the line number of code and the number of login statements, LPS, for each project, and the log density in the 1,000 lines of code as well. Projects are from different domains, are developed by different teams, and incorporate different logging practices. Also, this project selection enables us to compare our research with prior work. Here I have a summary of our results, and there are 3 different approaches compared with their precision, recall, F measure, and balance accuracy. So I just have formulas for the reference for each metric. So the general trend is as follows. OREO is a state-of-the-art clone detector, just a general purpose clone detector. LACC is our first log ever clone detector, and LACC Plus is the improved version. The general trend on how the methods perform is observable on the BA or balance accuracy metric as the values increase for our approach compared to the OREO. So in summary, our approach brings a 15.6% improvement over OREO. So in summary, because our approach, the log-aware clone detector or LACC Plus performs log-aware feature selection and calculation, it understands the log feature changes while processing the source code, and it achieves a higher log prediction performance. So now after I discuss the log location prediction based on the experiment results for predicting the location of log statements that I just showed you, we notice it is a valuable research effort to explore whether it is also possible to predict the location and the log statements description as well. And here is an example of the log description. In the toolchain, we initially extract, so this is a toolchain for log description prediction. Initially, we extract, again, the source code definitions with logging statements, and then we perform log-aware clone detection, which is the work that we have done in the previous section. Laterally, we also have a NLP-CC. So NLP is a natural language processing deep learning model, which basically predicts the log statement description and is trained on the logging descriptions available in the training set for each project. During the testing phase, we first find the clones of the unlocked method by using LACCP and user log description as a starting point fed into the NLP model. Then NLP model suggests a set of log descriptions, and we then calculate Blue and Roach scores to evaluate the performance of the log descriptions. So in this slide, I have some details of the internal implementation of the model. I just try to briefly review very quick. So the general idea is considering a sequence of tokens in LSD, which is a log description. The language model statistically estimates how likely a token is to follow based on observing the prior tokens, which comes in equation 1. And equation 2 states that the goal is to maximize the probability of observing a token based on the prior tokens. And finally, in equation 3, we have all the probabilities for all different tokens in the vocabulary of the log descriptions. This vocabulary comes from the training set of the log statement descriptions. And based on we have the softmax probabilities, meaning that we assign a probability to each next token, and then they are sorted, and the highest probability token is selected as the next token. So actually, to make this more understandable, and that how the NLP model can suggest LSTs, I provide just the following real example that I have picked from the Cloud Stack project. We have the following LSTs, as you can see at the top, for in the training set, which is successfully deleted condition appears 1 time, elastic store volume successfully deleted appears 3 times, successfully created floating IP appears 1 time in the training set. Because in the training set, the token deleted appears 4 times in total right after the token successfully, as you can see here, whereas created only happens once. Immediately after successfully, the NLP model assigns a higher probability for observing deleted after successfully. During testing, the retrieve LSTs from the clone per MDI is successfully created floating IP, and the original LST that we are aiming to predict is successfully deleted floating IP. Thus, with this NLP approach, the NLP model allows us to see high probability next tokens that appear in the training set that might not necessarily happen in the LST retrieved from the clone pair, and improve the log statement description prediction. And yes, I explained that. And then I have some, again, summary of results. And in addition to what I discussed, we also have a new set of measurement. So what I discussed was to predicting the token NLP1, the next token based on the one prior token. NLP3, so there has been also research, we also have done research that shows that the LSTs, or logarithm description, are sequence of natural language processing. Thus, we also experimented with predicting the next token based on the 3 prior tokens, or NLP3, which is an extra data point here, not only the prior tokens, but the 3 prior tokens. And then I also here have the blue and rouge scores. Blue score explains that how many of the tokens in the predicted LSD appear in the original LSD, which is similar to the precision that we discussed for the log location prediction. And rouge calculates that what percentage of the tokens from the original LSD appear in the predicted LSD, which is similar to recall. So overall, the scores for NLP1, no NLP, NLP1 and NLP3 are included side by side for each project. The NLP model improves these scores across the board. In summary, blue and rouge scores are improved for 4.5%. So to summarize, log location and description prediction with log-aware code clone detection, we propose the log-aware approach for automating the log location and its description. And we have the first part actually published. The second part is under review, which is for the log description prediction. So now this comes actually the third part of my presentation. I'm actually 22 minutes in. If there is any questions before I move on to the third part.
So,
Could I ask?
yeah, please go ahead.
So I just want to be clear. You mentioned a while back that 98% of clones had a log statement if the other thing in the clone pair had a log statement. I think that's roughly correct. Were those clones detected by the log-aware method or by some other method? And the reason I'm asking is that it seems to me if it was the log-aware method, that might rather contaminate the result.
Yes, so what I did was actually after detecting them, I deleted all the log statements and then read on it, meaning that I wanted them to be cloned regardless of the logging statements. Does it make sense?
Okay.
Meaning,
yeah, good.
So I had a question about, I guess I'm a little bit, if you go a little bit higher level. So can you tell me how a developer will use the tool to, so you're trying to predict where the log statement will be and what will be in the log statement?
yes.
How it's going to be used in the life cycle of development of a software?
So the way that actually these tools are implemented is as a recommender tool. So one way to implement it is as the plugin. There are some similar tools as they do, like as plugins into IDEs. For example, as that you are developing a code, there can be an background task which is running, and then you have the project is the code base linked in that your project in your IDE, and the tool in the background is looking for finding the code that you are developing and find its clones, and it tries to find if it's possible to find a method which is similar or like it's a clone of the code that you are currently developing. And based on that, if it finds a login statement, it can suggest that login statement to be added also in this newly developed source code, and the developers decides as well.
Oh, okay. Okay, now I see it. So you detect clones of code, and then you can
Yes.
tell the developer, oh, you are kind of following the same logic, or if not verbatim, but maybe the same, at some level of cloning, some other logic, but you are missing logging statements.
Yes, yes.
Okay, I see. Okay, thank you.
Okay, so I guess I will continue with the third part, which is natural language attributes of log files to leverage them for automated log analysis. We partially actually leverage the natural language processing attributes in the log descriptions when we use the NLP model. And now I extend that to the log files, which are the product of the runtime execution. So in this part, our main hypothesis is that our software logs natural and local. Thus, our research is in the area of natural language processing, or NLP. Let's first define natural and local attributes for software logs. Natural means that logs follow similar token patterns as natural languages such as English, as they are both applied by humans. And local, on the other hand, means that the appearance of tokens or words can be specific to their corresponding languages and projects. Lastly, the benefit of our approach is that the defined NLP attributes can be leveraged for automated log analysis, such as anomaly detection. We navigate our research through 6 research questions listed in this slide to validate our hypothesis. Research question 1, 2, and 3 are concerned with the naturalness of the logs and evaluate the regularity, project specificness, and Zipf's law for 8 different system logs, such as HDFS logs, Spark, and Linux logs, and compare it with the natural language text, such as Wikipedia articles. Research questions 4 and 5 evaluate the localness of the software logs by showing that logs are endemic and specific to their corresponding software projects. And finally, the research question 6, we show the benefits of our approach in detecting anomalous log lines with an NLP trained N-gram model. Here, I quickly present some of our findings. And the research, the result for research question 1 shows that the entropy values for logs in box plot versus English text entropy is in blue line. Entropy is a measure for regularity and repetitiveness, and the lower the entropy, the more regular the log file becomes. As we see here, the entropy values for different N-gram models are lower for logs versus English text, which means that logs are more regular and repetitive than common English text. The result for research questions 2 and 3 also verify this finding and show intra-project regularities and more frequent high-rank tokens in logs versus English. Thus, our finding is that logs are natural even more so than common English text. In this slide, the results for research question 4 shows that a higher percentage of tokens are endemic for system logs. Endemic tokens are the ones which only appear in one system log. The results for research question 5 shows that the non-endemic tokens have the tendency to appear in some specific system logs more than others. In other words, they are more specific to a particular system log. And finally, research question 6 shows our tool chain for a system that is utilizing NLP model trained on normal logs and can effectively detect anomalous logs during the testing phase, as these logs result in higher entropies. Thus, we utilize effectively NLP approaches for automated log analysis of logs. The key takeaway from this part is that because we showed logs are natural and local, we enabled to apply NLP features for automatically detect problems from system logs. This expedites developers and practitioners' troubleshooting efforts. So I'm going to make a quick transition to something which is related to that, but slightly different. So if there any question with regards to this part, otherwise I will continue. So now with regards to that, when we showed that logs are natural and local, we're going to use those attributes and evaluate the logging in distributed systems. So in this study, we evaluate the cost, the quantitative cost of logging in terms of computation time and storage overhead, and we evaluate how that's connected to different verbosity levels and the amount of information gained from logs. Information gain here is a similar concept as entropy values. And then we evaluate what happens to logs in case of a system failure. So here, the table summarizes the benchmark used in the experiments along with their characteristics, such as being CPU or IO intensive, and if the computation happens iteratively. During the benchmark selection, we were deliberate to include a variety of benchmarks, such as sparse conventional benchmarks, such as word count and page rank, and also machine learning ones, such as gradient boost classification and linear discriminant analysis, which is short for LDA, which is a clustering approach. So here I have some results for the execution time and storage overhead. The top row shows the computation time for different benchmarks for different log verbosity levels, such as logging off, info level, and trace level. And the second row shows the storage overhead of logs. Overall, we observe an average 8% increase in the execution time and 268 times overhead in the storage when the trace level log is enabled versus the info level. And the CPU intensive workloads suffer more from a higher degree of logging. So now let's talk about the log effectiveness. In this log estimate example on the left, log consists of two parts, static part in blue and the dynamic content. The static content of log estimates originates from the source code, and dynamic content is the value of variables that are printed in the log files as the system is running. And the common perception is that higher degree of logging translates to more effectiveness of the logs. For example, logging in trace level is more informative than info level, which we argue this assumption might not completely hold true. Our experimentation shows that although trace level generates a larger volume of logs, trace data does not provide a noticeable higher entropy, and hence does not necessarily carry higher information gain and effectiveness when compared to less verbose log levels, such as info level. The implication is that we presume trace logs show comparable information gain or IG to info level because they contain higher repetition rather than unique dynamic values. Thus, we continue that study with failures. So because logs are widely used for failure diagnosis, thus we evaluate the information gained from logs in failure scenarios. We design a framework to inject different types of distributed failures and measure their impact on logs and how the information gained from logs changes in the presence of the failure. We categorize the distributed failures in four main categories: compute node failure, storage node failure, communication interference, and combined failure, which can be a combination of multiple failures. We observe that failures result in a region of high entropy values than normal logs in the log files, and different runs show extended computation time and additional logs related to the failure. Computation time of CPU intensive application suffers more from compute node failures than IO intensive benchmarks and so on. So the implication is sudden changes in the entropy values of log records can signify information gain associated with a failure. This information gain can be leveraged for pinpointing the failure from the logs. Thus, for debugging, we are more interested in the regions of the logs with high entropy than logging in trace level. So with that, I actually also summarize and conclude the session that basically overall, we have performed a comprehensive survey, and then we have done log location and description prediction based on code clones and learning deep learning approaches. We showed that logs are natural and local for the software system, and then we use that attribute for performing logging cost analysis and information gain for distributed systems such as Spark. The pending future work is log prediction. On the log prediction side, we can continue with detecting the verbosity level and also include variables in the log estimate. That's still work in progress. We can also apply transfer learning for call-stop problem. There are many projects which they have a really small code base, so you might not be able to find clones easily in the code base. So the idea here is we can train the model on the other projects or a comprehensive set of code base, which we can, for example, get from Git repositories of GitHub. And then if the models are trained on that, then we can transfer that learned model to new projects. And then the other item can be constraint-based logging versus matching the developer's habits. Currently, many of the automated logging approaches work to mimic developers, meaning that we try to see if a log statement has been placed by developers and find similar code snippets. But I would see value in logging not to mimic the developer's habits, but to have a constraint in mind, meaning that I want to disambiguate this function, or I want to make sure every, for example, one line or one method out of 100 iteration is logged. So I have a sort of a minimalistic approach of how much is logged. And then the next step for the NLP models is the application of NLP, the new ones, the BERT model for log parsing anomaly detection through logs. That also comes after we showed that the logs are natural and local. So we can apply the new advances in natural language models for automated analysis of logs. And with that, I would be happy to take questions.
Questions? You can just turn your camera on and ask your question there directly. Yeah. Yeah, Mark?
Hi, yeah.
Sorry,
Great talk, Sina.
thank you.
Really interesting. So yeah, you said, okay, so NLP BERT at the end. I was wondering what NLP model are you using earlier on, because you just said very generally.
So
NLP.
early on, actually, I used the Ngram models. I started with Ngram models, and then I used the deep learning NLP models, neural nets.
So just
the,
doing
or
deep
the
neural network
RNN.
on
So
Ngrams?
initially I used Ngram models, which is a statistical model.
Yeah,
And
okay.
in the
It's not
second
words
phase,
of Eck or something like that.
sorry, can you repeat?
It's not words of Eck or something specific like that. It's a
No, I just initially used a traditional statistical model, and then I progressed to the deep learning neural nets, which is RNN. And now actually the BERT is the newest version. I think that also something that I wanted to ask your opinion on. How you think the performance would improve of applying a new improved BERT model?
Yeah, no, BERT's great. It depends on what it's pre-trained on and how the language matches. So that's something I was going to ask you, I guess, if they're applied on other natural language things, will they really apply here? How did you pick the 1 versus 3 look back window size?
So I did some experimentation actually. So the thing is there are some concerns here, like constraints here. So initially I took only one, and then I tried to use the sequence, the sentence level structure. And then I noticed if you go really higher, so the way that it works is if the length of the description is less than 3, it adds padding. And in general, the LSTs are shorter than full English text. So 3 is sort of a sweet spot. I mean, if I go too larger, it adds noise because there are so much padding, like for the descriptions which are really short. And if you go basically like I had the 1 and then I picked 3, I can actually add again like other data points like 4 or 5, but when I saw the 3 works well, then I stayed with 3.
Yeah, it would make sense. It wouldn't be super long because log things are short. The other thing I was wondering about, and then I'll let other people ask, is you're saying using entropy, and obviously entropy is a good way to measure the amount of information in a thing, but is it the best measure for what you're looking for here? Like, is it possible that something more customized to logs would tell you more than entropy? Like certain logging of certain events is more important than others, right? Is there kind of any idea that you can use weighting of the type of event to tell you whether the logging is good or
Yeah, so actually, so the entropy that gives me, so the way that I approached this problem was when you train on normal logs, on the basically that gives you the normal language of the system. And when a problem of failure and anomaly happens, that's sort of a language which is different from a normal language of the system that results in higher entropies. But certainly, actually, I would be willing to see if I can combine that with other metrics to improve it. What was the thing you said, the weighted approach?
I don't know, I was just wondering if because the entropy could be that it's just not repeating, and so all the log messages are different. It might have higher entropy than one where all the log messages were similar, right? But then that wouldn't necessarily be more informative to a human being reading it. And repetition can actually be useful because you're logging every event that's important, critical event.
Sure. So in this approach that I am actually using, the thing that I observe is when you, so there are two things. So what I also observe with the trace level is that, okay, I received a huge number of logs, And I would also assume that that also resulted on the same baseline entropies, but more repetition. So there was actually some research that you might have repetition. Actually, there is a prior work that has done that through a compression of logs, meaning that they actually mentioned that, okay, the thing is being repeated, but the pattern sequences that are being repeated are different if there is a problem in the system, meaning that if you compress that region, it compresses less. So what I did actually was I was actually running a window of log, meaning that I experimented with different windows of sizes, and I measured the entropy through that entire region of the log.
Oh, okay. So the pattern amongst log entries would be important too. Okay.
Yes, but I would certainly look into that to see. But that's a good point. So you're talking about the order of the logs, not only being something outside the language, but also how they repeat, the sequencing of the logs.
Yeah, it's just saying one of those other ways to do it, but great. Okay, thank you.
Any other questions?
Sina, I had a few comments.
Thank you. Go ahead.
Yeah, so I think I understood roughly what you've done. Most of the questions were regarding maybe the higher level perspective. So like starting with part one of the presentation, you showed us a summary of your survey in the form of a tree, if we can call it that. It's some kind of a taxonomy or categorization of topics.
Yes.
It wasn't super clear to me, what are the open problems in this space? So some short list of important open problems would have been helpful. And that would have helped set the stage for part two and part three, where we get to some fairly technical content. There are long formulas in some of your slides. And I'm not sure I really understood the impact of the work. So for example, in part two, my impression is that you found a way to identify clones.
Yes.
Did I understand correctly or incorrectly? So when you look at metrics like accuracy, that's a metric for a classifier. High accuracy is good, low accuracy is bad. Okay, so if what we're really doing is trying to identify clones, then this seems to me more like just mining software repositories and less specific to logging itself. And so I was wondering, I mean, clearly the application here is if you find a clone, okay, you may want to alert the programmer that there are some missing logging statements, but also this makes me wonder why there are so many clones in the code in the first place. I mean, can the code not be modularized, and then could the logging statements not be placed inside some reusable sub-procedure? Why are we helping programmers create these clones and then instrument them with logging statements that will look very similar across different clones? So are there alternative ways to solve this problem of making sure that we don't have missing log entries other than the solution that you proposed?
Yeah, so the solutions actually that the approaches that are trying to automate the logging process. Now I'm focusing on the learning approaches. All of them are pretty much that I have seen in the literature aiming to get a set of training which is logged. So there are different levels of logging. Some people look at it in the code block level. Some people look at it at error log messages, for example, in cache clause and etc. They try to extract source code features from those methods and then train a model. And then when you give it a new unlocked source code, then it tries to match the features of the new piece of code, which is unlocked. And if it finds a mapping, then it suggests the log statements. That is pretty much roughly how all the learning approaches work. So the first part of actually clone detection is sort of similar to the learning, meaning that the clone detection methods have been around for a long time. So I would argue that because clone detection has been, there are so many mature clone detectors which are a part of a software maintenance process are fully in use. So what I'm doing here is actually I'm leveraging what is already being established in the sense of and it's also already integrated in the platform. The other benefit is because I'm matching it with the code which already exists, that gives me an extra context. If you're only training your model on a training set and then you're trying to test it, if I give you a new code, you do not have the context from the clone pair. So that limits you for predicting extra details of a log statement. For example, my description, a log statement description builds on the first part, which is you find a clone pair, and then you start a description from the clone pair as the starting point for suggesting description. The same thing goes for as I showed, that many of them actually match in their verbosity level. So I would argue that this approach gives us more context to also predict more details of the log statements compared to, so meaning that the approach that you select features to find the clones is very similar in concept to learning to log. It's a learning approach for sure. And then it also adds you it gives you the extra context that you can leverage for further prediction of the log details. Regarding that part, actually, that you said why there are clones, some of them actually are similar code snippets, meaning that it's not always a bad thing. Some of them are the artifact of copy pasting. Yes, meaning developers actually have a module which they develop, or sometimes actually not even in the same project. It might be even in a different project, meaning that you might have a new project which is built on the previous project and sort of inherits some of the implementation. But code clone detection is a part of a sort of a large chunk of software maintenance, and some of them are actually causing bugs. So it's a double-sided sword, meaning that some of them are positive at the same time as some of them are negative. Did I answer your question?
I'm still thinking about that one, and I had a related question about part 3. So, what is your high-level figure of merit here, right? Like looking at the accuracy of some tool that can find clones is a kind of an indirect way of measuring how effective is my logging. So what is the final figure of merit that we're trying to improve through all these techniques and optimizations? Is it trying to decrease development time, or is it some dollar figure, or some measure of code reliability, number of bugs per 1,000 lines? What are we trying to do here?
So I would say just the qualitative is it's providing suggestions for developers is useful to save time and effort for sure. Actually, I had a case study that there was so it's in the slides, was later in the slides. I had a case study that I found a piece of code which was developed later than the original snippet of the code, which basically was missing a login statement, and it went through 2 iterations. Like the first iteration, the developers noticed it's a missing login statement, and they add a login statement. In the first try, even they get it right. So, and then they went to the second iteration and they added some extra details into the login statement. So that thing, when it becomes functional, it's basically saves time and efforts, like development effort. And actually there has been some research that has shown quantitatively developers spend a significant amount of time on updating logs. This is actually a sort of a interactive or a passive approach as a suggestion. If you make it proactive, you can tell me I have a code base, and then you proactively without asking developers, you you find the clones and copy them as directly to a new piece of unlocked code. But the main application is the as a recommender or a suggestion tool. That's how I envision it, as a plugging to IDE tools.
So what is the figure of merit? You're talking about applications, but what I'm asking is how do we, for example, you mentioned log effectiveness. How do we quantify log effectiveness?
Log effectiveness, the way that I quantify it is on the on the debugging effort, meaning that how much it helps you to debug better in case a failure happens. The way that I have measured that, it's based on assuming all. So what I have done is I actually, for my testing and training, I removed the logging statements from the snippets of the code which have been logged. So meaning that I assume developers, based on developers' knowledge, all these logging statements should have been logged. So if you don't log them, you are missing some debugging information. So the effectiveness is on the debugging, and the more I can predict those logs, they should exist with a higher accuracy, my effectiveness is higher compared to not having it.
So you are able to put a number on that.
Yes. So the precision, the accuracy, and the recall is basically based on developers' perspective, meaning that all those codes, what I have done is I have extracted them, and then I have testing and training, and then I keep the logs in the training and then remove them from the testing. So assuming all these methods should have a logging statement based on developer's opinion, the more I predict is the metric that I evaluate it. But I also mentioned, actually, this is the common approach, meaning that that's what research has done so far to mimicking developers' habits. But I would see that it might even become more useful to have a constraint-based logging. Not developers, because there has been some research that developers make so many mistakes in the code, and even they forget to log in many places because it's not a feature code. So the logging code has more issues, like the code churn rates and etc., compared to the feature code. So the idea here is actually we might not be necessarily relying on developers' opinion because they make mistakes. So if I have a constraint, that meaning that I guarantee that, for example, based on this constraint, I have logged everything, that might become a stronger avenue, not only developers.
Okay, thank you. Thanks for that nice talk.
Sina?
Yes.
And unless there's others, one thing I'd like to follow up with from Wojtek. You said you remove the logging statements and then you effectively determine your log generator determines where log statements should go.
Yes.
Is that a different trained model for each of the different code bases you're playing with?
No.
Or
So
is this is a common trained model? Yes.
yes. So basically, the way that actually, when you, for example, have a general purpose clone detectors, the way that they train them on a massive set of projects. I mean, randomly selected from, for example, GitHub. The last one I checked is like 50K project, and the idea here is to have a universal clone detection tool, which you can apply to any sort of project in for example, that programming language, and it can detect if these two pieces snippets of the code are similar as clones or not. So the benefit that comes from my approach is not on the training, meaning that I assume I use a universal model. So if you train it on the current available code base of the software development systems, which is available at the moment, then when you create a code which comes in future, it's very likely, if you have a universal model, you can match it with the already existing code in the code base. The benefit of mine comes because it's log aware. So when it calculates the features, it knows that these are the login statement in the code, and it does not allow them to change the feature metrics of the code, so they become so different that they cannot be matched as clone pairs. because out of my study, I showed you that there are so many false positive and false negatives, meaning that and the use case is when you're developing a source code, there is no logging statement in it, but you are trying to still match it with the code which has a logging statement in it. That causes the feature metrics to become very different. So many times you miss them because they don't have equal features, but because the logging statement is different, we exclude that because that's not a feature code, it's a bookkeeping aspect of the source code.
Okay. Good. Thank you.
Excellent. So Anil, yeah, we are almost out of time, but any last questions, comments? Okay, thank you, everyone. I would like especially to thank Sina for the nice presentation.
Thank you.
Great job. And thank you, everyone, for attending today. And see you next week.
See you. Bye-bye.
Thank you. Yeah, bye-bye.